Welcome to Study Loop.
This is problem 119 of chapter 7.4 of Vector Mechanics for Engineers, Statics, and Dynamics. So there is a cable that goes from A to B in a simple beam A', B', both with a length L, and both subjected to the same vertical loadings P1, P2, P3, and Pn. So for this problem, we are going to show that the bending moment at C' is equal to T naught H. So the first thing we are going to do is draw a free body diagram of the whole problem from A to B. We're going to include the reaction forces at A. AY is in the positive Y direction, and T naught is in the negative X direction, and also the reaction forces at B. BY is in the positive Y direction, and T naught is in the positive X direction. Also, the horizontal distance from A to B is L. The horizontal distance from A to E is X. The vertical distance from B to A is A, and the vertical distance from E to C is H. So we're going to let the sum of moments around B due to all the loads be this symbol, and it's going to be the moment produced by the loads P1, P2, P3, Pn about B. So the first thing we're going to do is the sum of moments around B and set that equal to 0. And this equals T naught times A, which is the vertical distance from A to B, minus AY times L, the horizontal distance from A to B, plus the sum of moments around B due to the loads. So we're going to simplify down and solve for AY, which equals 1 over L times the sum of moments of B due to all the loads minus T naught times A. And we're going to need this equation later on. Next, we want to try to obtain the length DE. So we're going to show a relationship. So L over A equals AD over DE. Simplifying, L over A equals X over DE. So DE is A over L times X, which we will also need later on. Next, we're going to draw a free body diagram from A to C. Again, X is the horizontal distance from A to C, and H is the vertical distance from E to C. This time, we're going to let the summation MC P1, P2 be the moment produced by the loads P1 and P2 about C. So we're going to do the sum of moments around C and set that equal to 0. This equals T naught times CE minus DE minus AY times AD plus the sum of moments around C due to P1 and P2. So this, we can plug in the DE and XY equations that we found above. So T naught times H minus A over L X minus 1 over L times the sum of moments B due to all the loads minus T naught times A plus the sum of moments around C due to P1 and P2 and set that equal to 0. Simplifying, T naught times H equals X over L times the sum of moments of B due to all the loads minus the sum of the moments around C due to P1 and P2. We're going to need this later on. Next, we're going to draw a free body diagram of the simple beam from A' to B', with all of the loads pointing downward, P1, P2, P3, and Pn. X is the distance from A' to C', and L is the horizontal distance from A' to B'. So we're going to do the sum of moments around B', set equal to 0. This equals negative A'y times L, the distance from A' to B', plus the sum of moments around B due to all the loads. We're going to solve for A'y, which equals 1 over L times the sum of moments around B due to the loads. Next, we're going to draw a free body diagram from A' to C', and again, the horizontal distance between A' and C' is X. So we're going to do the bending moment around C', and this equals A'y times X, which is the horizontal distance, minus the sum of moments around C due to the loads P1 and P2. So simplifying, we can plug in the A'y, which we just solved for. So the bending moment of C' equals X over L times the sum of moments around B due to all loads minus the sum of moments around C due to P1 and P2. So we know that this is the equation that we saw for earlier, which equaled T naught times H. So we know the bending moment at C prime equals T naught times H. So therefore, the bending moment at C prime on the beam is equal to the horizontal component of the tension force in the cable AB times the vertical distance from C to the chord between A and B.